Section 1 Introduction. Our paper primarily focuses on an emerging area within image synthesis and editing technology, particularly on the application of text-to-image diffusion models. These models have been fine-tuned with billions of image-text pairs, leading to their remarkable ability to generate realistic and diverse images from given text inputs. In addition, they found use in multiple applications, including image-to-image translation, controllable generation, and even personalization. One of the newest and most exciting areas of exploration is extending these models' capabilities to more complex visual tasks, particularly beyond 2D images. This involves adapting the knowledge of pre-trained text-to-image diffusion models to more intricate, high-dimensional visual generative tasks, without needing to modify the diffusion models or use specific training data for each modality. We theorize that many complex visual datasets, such as videos and 3D scenes, are essentially sets of images held together by certain rules of consistency specific to each modality. For instance, a video can be thought of as a series of frames, which require a temporal consistency, while a 3D scene consists of multiple views that require consistent perspectives. However, standard image diffusion models don't inherently ensure this consistency between images when synthesizing or editing. Therefore, when applied to these complex datasets without considering consistency, the results can be noticeably disjointed and incoherent, as is demonstrated in figure, patchwise crop. In an effort to address this issue, we're introducing an alternate approach, called score distillation sampling, SDS. SDS allows for the optimization of any differentiable operator, capitalizing on the powerful generative capabilities of text-to-image diffusion models. By treating generative sampling as an optimization issue, SDS can distill the learned diffusion density scores. We extend this concept with our proposed method, Collaborative Score Distillation, CSD, which enables consistent visual synthesis. The key aspects of our method are twofold. Firstly, we extend SDS by using Stein variational gradient descent, where multiple samples share knowledge from the diffusion models to achieve consistency. Secondly, we introduce CSD Edit, an effective tool for consistent visual editing that integrates CSD with a recently proposed instruction-guided image diffusion model, Instruct Pix2Pix. We showcase our method's adaptability in various contexts, such as editing panoramic images, videos, and reconstructed 3D scenes. For example, when editing a panorama, CSD Edit optimizes multiple patches of an image to ensure spatial consistency. We also demonstrate that our approach strikes a better balance between maintaining consistency from the source to the target image and preserving instruction fidelity, compared to other methods. In the context of video editing, CSD Edit considers multiple frames during optimization, resulting in videos with temporally consistent frames. Additionally, when we apply CSD Edit to 3D scene editing and generation, we encourage consistency among multiple views. Section Summary. Text-to-image diffusion models have been successful in synthesizing high-quality images from text inputs, but they lack the ability to ensure consistency when generating complex visual data like videos or 3D scenes. This paper introduces Collaborative Score Distillation, CSD, a method that extends the capabilities of text-to-image diffusion models to achieve consistent visual synthesis. By leveraging multiple samples and optimizing intersample consistency, CSD enables spatially and temporally consistent image and video editing, as well as consistent editing and generation of 3D scenes. Section 2 Preliminaries. Let's explore the basics or preliminaries. To begin, we'll delve into diffusion models. Imagine you're trying to create a generative model using these diffusion techniques. The process consists of two steps, a forward process and a reverse process. In the forward process, we gradually add a type of noise, specifically Gaussian noise, to the initial input. This process is represented by a function we call Q. The reverse process, represented by a function we call P, is all about gradually removing this Gaussian noise. To dive deeper into the specifics of the forward process, we can say that the function Q, at any given point in time, t, depends on the initial input and a few predefined constants, denoted as sigma_t and alpha_t. These constants are defined in a way to make the modeling process more effective. Here, alpha_t is specifically calculated from sigma_t by the relation alpha_t squared equals 1 minus sigma_t squared. With the passage of time, the reverse process also begins to behave like a Gaussian function. This transition is facilitated by a posterior function q, using an optimal mean square error, MSE, denoiser, which is denoted by the symbol _phi. We then train a U-net autoencoder, represented by the symbol epsilon_phi, to minimize an objective function. This function involves a weighting function w, t, and the difference between the autoencoder output and the noise, squared. Text-to-image diffusion models take this one step further by estimating noise conditioned on a text prompt. To improve the quality of generated samples during the inference process, we use a method called classifier-free guidance or CFG. Here, we introduce another parameter omega_y that modifies the output of the autoencoder. We have found that by increasing the value of this omega_y parameter, we can make the output better resemble the text prompt, but at the expense of diversity. This paper also explores the concept of instruction-based image editing using a method called instruct_pix2pix. This technique uses diffusion models to edit or stylize images based on given instructions. This method uses the CFG technique to ensure the generated image remains faithful to both the source image and the text instructions provided. We introduce another parameter omega_s which allows us to control the degree of fidelity to the source image. By appropriately adjusting omega_s and omega_y, we can ensure the image generation process is influenced by both the source image and the text instructions, resulting in an image that is a blend of both. Section Summary. In this section, the authors introduce diffusion models for generative modeling, which involve a forward process that adds Gaussian noise to the input and a reverse process that denoises the Gaussian noise. They propose training a U-net autoencoder to minimize a specific objective and use classifier-free guidance, CFG, for higher quality sample generation. They also discuss the application of diffusion models in instruction-based image editing, where they use fine-tuned stable diffusion models with source images, text instructions, and edited images to enable instruction-based editing. Section 2.2 Score Distillation Sampling. In Section 2.2, the authors introduce score distillation sampling, SDS, a method for generating samples that distills knowledge from text to image diffusion models. SDS can be used with any differentiable image generator, such as neural radiance fields or the image space itself. The idea is as follows. Consider an image that is rendered by a differentiable generator with a certain parameter. SDS works by reducing the density distillation loss, which is a measure of the difference between the posterior of the image rendered by this generator and the text conditional density. This difference is measured using the KL divergence. For practical implementation, SDS updates the parameter by randomly picking time steps and forward propagating the image with some noise to compute the gradient. The authors note that a computationally expensive component, the U-net Jacobian, is omitted because it degrades performance when the noise level is low. The range of time steps and the scaling factors are chosen carefully to balance the noise levels and image generation quality. In Section 2.3, the authors discuss Stein variational gradient descent, SVGD, which is a method for approximating a complex target distribution from a simpler source distribution. The goal is to minimize the KL divergence between these two distributions. The essential aspect of SVGD is to find the steepest descent direction of KL divergence between the source and the target distribution. This descent direction depends on a smooth vector function. The authors highlight the role of Stein's identity, which states that the difference between the source and target distribution is zero when we consider the target distribution in the expectation term. In SVGD, the choice of the function used to calculate the steepest descent, the critic, is crucial. The authors suggest using a function from the reproducing kernel Hilbert space, RKHS, for this purpose, which provides a closed-form solution. SVGD also provides the update direction to move our approximation closer to the target distribution. The SVGD update comprises two parts. The first moves the approximation toward the high-density region of the target distribution, with direction smoothed by other approximations or particles. The second part acts as a repelling force that prevents the particles from collapsing into a single mode. The authors suggest using the standard radial basis function, RBF, kernel for these calculations, which uses a measure of the distance between 2 points. Section Summary. In the proposed score distillation sampling, SDS, method, the rich knowledge of text-to-image diffusion models is distilled to optimize any differentiable image generator. SDS minimizes the density distillation loss by updating the generator's parameters using randomly chosen time steps and forward passes with noise. Stein variational gradient descent, SVGD, is a method used to approximate a target distribution from a simpler distribution by minimizing the KL divergence. It involves steepest descent of the KL divergence between the source and target distributions, where the choice of the critic function is crucial. SVGD updates the particles by moving them towards the high-density region of the target distribution and preventing mode collapse using a repulsive force. Section 3 Method. In this section, we're going to discuss our approach, Collaborative Score Distillation, CSD, which we've developed to facilitate consistent synthesis and editing of multiple samples. To start, we'll show you how we came up with the collaborative score distillation method by using Stein variational gradient descent. Following this, we'll reveal our effective image editing technique which relies on CSD, namely, CSD edit. This method enables us to edit multiple images coherently based on specific instructions. Finally, we'll showcase a range of applications for CSD edit, including editing panoramic images, videos, and 3D scenes. We begin by considering a set of parameters, which we'll denote as theta. These parameters are used to generate images. In a similar vein to the SDS method, our aim is to refine each of these parameters, theta, by harnessing the smooth densities derived from the diffusion model. This is accomplished by reducing the Kullback-Leibler divergence. However, while SDS tackles this process individually, CSD handles it via Stein variational gradient descent, ensuring that each parameter, theta, is updated concurrently with all others in the set. During each update, CSD generates random samples and updates each parameter, theta, based on these samples. Each parameter update is influenced by the other parameters, meaning the scores are blended with weighting factors that reflect the degree of similarity between samples. Samples that are more alike tend to share more score updates, while those that differ exchange less score information. This strategy prevents the so-called mode collapse of samples, as the gradient of the kernels acts as a repelling force. It's important to note that this method doesn't make assumptions about the relationship between the parameters, theta, or their order, other than that they're a set of images to be synthesized coherently. As such, CSD can be used with any image generators, and it's also compatible with text-to-3D synthesis in DreamFusion, which we'll compare later on. In essence, CSD is an extension of SDS that can handle multiple samples. When there's only one sample, CSD is equivalent to SDS. Section Summary. In this section, the authors introduce Collaborative Score Distillation, CSD, for consistent synthesis and editing of multiple samples. They propose a method using Stein variational gradient descent to update each parameter in sync with other parameters, allowing for coherent editing of multiple images. CSD ensures that similar samples exchange more score updates, preventing mode collapse, and can be applied to various image generators and text-to-3D synthesis. Section 3.2 Text-Guided Editing by Collaborative Score Distillation. In this section, we discuss an approach called Collaborative Score Distillation, CSD edit, which we use for editing visuals, guided by text. The method uses source images and corresponding parameters, and aims to generate new target parameters. The objectives are threefold. 1. Ensure that each edited image follows the instruction prompt. 2. Retain as much of the source image's semantics as possible. And 3. Ensure consistency among the edited images. To meet these objectives, we start with the source image's parameters and update them using the CSD approach, considering a noise estimate from an instruct-pix2-pix model. However, one challenge we encounter is that the resulting edited images often appear blurry, losing detail from the original image. We believe this is due to the random noise subtracted during the score distillation process, which can eliminate undesired details of the source images. To address this issue, we adjust the noise prediction term to improve the consistency between the source and target images. The subtraction of this random noise when calculating the gradient is a key factor, as it aids in optimization by reducing gradient variance. Thus, we revise the optimization process by transforming the random noise into a better baseline function. Considering that our objective is to edit an image with only minimal guidance from text instructions, we set the baseline as the image conditional noise estimate from the instruct-pix2-pix model. This is done without providing text instructions on the source image. Our CSD edit process then proceeds as follows. We calculate the gradient of the loss function of CSD edit with respect to the target parameters. This calculation takes into account the sum of a specific function applied to pairs of images and the change in an estimate function, along with the gradient of the specific function with respect to the images. This estimate function is calculated as the difference between the noise estimates of the instruct-pix2-pix model for the target image and the source image, respectively. In the next section, we will confirm our findings about the impact of baseline noise on image editing performance. We find that CSD edit offers an alternative method to use instruct-pix2-pix in image editing without any fine-tuning of diffusion models, by posing an optimization problem. Section Summary. In this section, the authors propose a text-guided visual editing method called Collaborative Score Distillation, CSD edit. They optimize target parameters to generate new images that follow instruction prompts, preserve the semantics of source images, and maintain consistency among the generated images. However, The current approach often leads to blurred outputs due to the subtraction of random noise, which removes important details. To address this, they adjust the noise prediction term and use a better baseline function to improve the optimization process. The authors also validate the effect of baseline noise on image editing performance. Overall, CSD Edit offers an alternative approach to utilize Instruct Pix2Pix for image editing without the need for fine-tuning diffusion models. Section: Panorama Image Editing. We aim to simplify and explain the technical concepts around image editing, video editing, and 3D scene editing that are presented in the given excerpt. We'll be focusing on the application of a process known as CSD Edit. Let's start with panorama image editing. Now, typically, models used for diffusion-based editing are trained at a fixed resolution, say 512 pixels by 512 pixels. When you attempt to edit a panorama image, which is a wide image with a large aspect ratio, the editing quality might not be as good. You could, in theory, split the image into smaller pieces and edit each of these separately, but this would lead to inconsistencies across the image. Refer to the figure titled Patch-Wise Crop in the appendix. Our solution is to use CSD Edit on the smaller sections of the image. We create these sections by sampling overlapping patches of 512 by 512 pixels, and then we apply CSD Edit in the stable diffusion latent space. Because the patches overlap, some pixels may be edited more often than others. To balance this, we normalize the gradient of each pixel according to its frequency of appearance. Moving on to video editing, 3 important aspects need to be considered. 1. Temporal consistency. The changes made in each frame should be proportionate to the original video across all frames. 2. Desired edits. The changes made in each frame should align with the provided prompts while keeping the original structure of the source video intact. 3. Quality preservation. After editing, each frame should still maintain its initial quality. To achieve this, we randomly select a group of frames and apply CSD Edit to ensure the temporal consistency of the changes across all frames. Lastly, when it comes to 3D scene editing, we're specifically looking at editing 3D scenes that are reconstructed by something called a neural radiance field, or NRF. This method captures 3D scenes using 2D images. Now, the straightforward way to edit these reconstructed 3D NRF scenes would be to replace the training views with edited views and fine-tune the NRF with these. But, you need to be aware of the consistency across these views. If there are inconsistencies, it can lead to blurred or unwanted artifacts, and this could disrupt the optimization process of NRF. There's a method known as Instruct NRF to NRF that performs editing on a subset of training views and updates them sequentially during training, but this can also result in inconsistencies. Our approach is different. We use CSD Edit to update the dataset with multiple consistent views. This serves as better training resources for NRF, leading to less artifacts and better preservation of the original 3D scene. Section summary. When editing panorama images, the quality often degrades due to fixed resolution training. To address this, we propose applying CSD Edit on overlapping patches of the image to achieve spatially consistent editing while preserving the original semantics. Similarly, when editing videos, we use CSD Edit on randomly sampled frames to ensure temporal consistency and maintain the quality of each frame. For editing 3D scenes reconstructed by NRF, we update the training views with edited views using CSD Edit to achieve multi-view consistency and improve the preservation of the source scene. Section 4.1 Text-Guided Panorama Image Editing. 4.1 Text-Guided Panorama Image Editing. In this section, we focus on editing panorama images using our method called CSD Edit. We compare its performance with different variations of Instruct Pix2Pix, a tool that alters images based on text descriptions. The first variation uses a simple method of reducing the image size to 512 by 512 pixels and running Instruct Pix2Pix on it. The second version incorporates multi-diffusion, an image editing process that modifies different parts of the image separately. To Instruct Pix2Pix, we refer to it as Instruct Pix2Pix plus multi-diffusion. We conduct our comparison on a collection of panorama images, which are images with an aspect ratio greater than 3. We then edit each image to reflect various artistic styles and different scales, referred to as guidance scales, omega_y. To measure our results, we use CLIP, a pre-trained model for evaluating images and text. We calculate 2 metrics: 1. Consistency between the original and edited images, and 2. Directional similarity, which assesses whether the changes in the text match the changes in the images. The details of our experimental procedure can be found in the appendix. Our results, displayed in a figure, show that CSD Edit balances well between maintaining the original image's consistency and accurately following the text instructions. Another figure gives a visual comparison between the different Panorama image editing methods. We found that while Instruct Pix2 Pix plus multi-diffusion can create images that are spatially consistent, they tend not to follow the text instructions as closely when we use a large guidance scale. You can find more visual examples in the appendix. 4.2 Text-Guided Video Editing. In our video editing experiments, we mainly compare CSD Edit with other existing zero-shot video editing methods that use text-to-image diffusion models such as Fate0 and Pix2 Video. These are methods that can edit videos without being trained on a specific task beforehand. To highlight the efficiency of CSD Edit, we also compare it with Gen 1, a top-tier video editing method that has been trained on a large video dataset. We use the same metrics as in the previous section to evaluate the alignment between changes in text and images. We also measure temporal consistency, or how smoothly the images transition from one to the next, using both clip image consistency and a measurement called LPIPS. We test these methods on video sequences from the widely used Davis dataset, with a resolution of 1920 by 1080 pixels. Details about the baseline methods and the setup of our experiments can be found in the appendix. Our quantitative comparison between CSD Edit and the other methods, presented in a table, reveals that CSD Edit outperforms the existing zero-shot video editing methods in terms of both temporal consistency and following the given text prompts accurately. A figure visually showcases the superior performance of CSD Edit in video stylization and object-aware editing tasks. Notably, CSD Edit's performance is comparable to that of Gen 1, even though it does not require training on a large-scale video dataset or any modifications to the diffusion model. Additional visual results can be found in the appendix. Section Summary. In the section on text-guided panorama image editing, the authors compare their CSD Edit method with different versions of Instruct Pix2 Pix. They evaluate the methods using pre-trained clip to measure consistency between source and target images, as well as the agreement between text changes and image changes. CSD Edit provides the best trade-off between consistency and fidelity to the instruction. In the section on text-guided video editing, the authors compare CSD Edit with existing zero-shot video editing schemes such as Fate0 and Pix2 Video. They also compare it with Gen 1, a state-of-the-art video editing method trained on a large-scale video dataset. CSD Edit consistently outperforms the existing schemes in terms of temporal consistency and fidelity to text prompts, even without training on a large-scale video dataset or modifying the diffusion model. Section 4.3 Text-Guided 3D Scene Editing. In this section, we delve into the outcomes of our text-guided 3D scene editing experiments. We mainly compared our method, known as CSD Edit, with a different approach called Instruct Nerf, or Indiana 2N for short. To make the comparison fair, we duplicated in 2N's experiment setup and fine-tuned the settings to replicate their results. To evaluate the results, we created images from fresh perspectives, ones not used during training. We then gauged the similarity of the generated images and assessed the differences between consecutive frames in the videos we created to establish their multi-view consistency. Additionally, we measured how faithfully the images reflected the original instructions by checking the similarity between the image and the text. We've provided in-depth explanations of our datasets and training procedures in the appendix. When comparing CSD Edit and IN2N, we observed that our method offered a greater degree of control over 3D Nerf scenes, allowing for fine-tuned adjustments such as changing facial expressions and altering scene styles, like making the scene resemble an animation. Notably, CSD Edit had two significant advantages over Indiana 2N. Firstly, it enriched the edited 3D scene with high-quality details by offering consistent training views during Nerf optimization, leading to sharper and less blurry outcomes. Secondly, it was superior at maintaining the semantics of the original 3D scenes, for instance, keeping the backgrounds or colors consistent, and allowing for subtle changes without disrupting the overall scene. Furthermore, we investigated the efficacy of CSD in text-to-3D generation tasks using DreamFusion as a guide. We trained a Nerf architecture based on coordinate MLP from scratch, utilizing text-to-image diffusion models. However, as the pixel space diffusion model that DreamFusion used wasn't publicly available, we turned to an open-source implementation of a similar model. We noticed that when using CSD for text-to-3D generation, the LPIPS distance worked well as a measure for the radial basis function, RBF, kernel. You'll find more details in the appendix. After setting a group of text prompts, we ran both DreamFusion and DreamFusion with CSD, and noted that both methods often generated similar objects. However, CSD frequently added more detailed elements, enhancing the poor quality outcomes from dream fusion. For example, CSD successfully got rid of blurry artifacts in the 3D nerf scene, often caused by inconsistent view distillation. We also found that CSD generated more coherent images when conditioned on view-dependent prompts used in dream fusion. You can find more examples in the appendix. Section Summary. In the text-guided 3D scene editing experiments, we compared our approach with Indiana 2N and followed their experimental setup and hyperparameters. We evaluated the results by measuring image similarity, multi-view consistency, and fidelity to the instruction. Our approach, CSD Edit, allows for a wide range of control over 3D nerf scenes, capturing high-quality details and preserving the semantics of the source scenes better than Indiana 2N. In text-to-3D generation tasks, CSD improves the quality of generated objects by adding better details and removing artifacts caused by inconsistent view distillation. Section. Ablation on the components of CSD. Our focus is on examining the specific components of our method, CSD, consistent score distillation. To do this, we conducted a study on video editing to illustrate the impact of our method. Specifically, we looked at how the communication between different video samples using SVGD, Stein variational gradient descent, affects the outcome. We compared results from videos that used SVGD to those that didn't. We discovered that when SVGD was not used, the video edits between frames were inconsistent. For instance, a red cap or a blue cap would appear on different frames, instead of a consistent red cap throughout. We also examined the role of baseline noise in CSD edit by using random noise. Here, the frames turned out to be blurry, and they lost their original structure, such as the sharpness of legs and backgrounds. In terms of related work, many have leveraged the successes of text-to-image diffusion models for different visual editing tasks, such as images, videos, and 3D scenes. However, these approaches face challenges when it comes to ensuring consistency in the edits for more complex visuals. These challenges include ensuring spatial consistency in high-resolution images, temporal consistency in videos, and multi-view consistency in 3D scenes. While previous works have focused on developing specific methods or fine-tuning models for these complex visuals, we've presented a new method that's not tied to any one type of media and that effectively maintains consistency between samples. Our method shares similarities with DreamFusion's work, which used score distillation sampling, SDS, to create 3D assets by utilizing text-to-image diffusion models. While SDS is flexible and can optimize a range of differentiable operators, most applications of it have been to improve the quality of 3D scene synthesis by introducing 3D-specific frameworks. There has been some use of SDS for other visual domains besides 3D scenes, but this has mostly been limited to image editing or generation. However, we want to emphasize that our primary goal isn't to enhance the performance of SDS for a specific task. Instead, our focus is on expanding its application in a new and meaningful way. To our knowledge, we are the first to focus our efforts on generalizing SDS. Our novel method successfully adapts text-to-image diffusion models for a variety of high-dimensional visual syntheses that extend beyond a single 2D image with a fixed resolution. Section Summary. In this section, the authors present an ablation study to demonstrate the effectiveness of their method. They compare the editing results with and without SVGD to verify the role of communication between samples, and also provide results when using random noise as a baseline to verify the role of baseline noise in CSD edit. The results show that CSD edit consistently edits a source video with a red cap on a man's head when given the instruction, give him a cap, but without SVGD, the edits between frames are inconsistent. Additionally, setting the baseline noise as random noise causes each frame to become blurry and lose the original structures. The authors also discuss related work and highlight that their focus is on generalizing the method rather than improving performance for a specific task.